Because the magnetic force is perpendicular both to the direction of the velocity of the charged particle and to the magnetic field, we have to use the right-hand rule to do that. You can see in this picture that I've formed the magic widget with my right hand. The way that I'm assigning it is that I put the force force will go on my thumb. That's usually what we're trying to find. You'll align your index finger with the conventional current. So I for current goes with I for index finger. Conventional current is going to be the same thing as the charge of if you have a single particle, the charge of that particle times its velocity. And we will align the three field fingers with the magnetic field B. So a way to remember that is B field goes on the bird finger B to B. Another way that you can remember that is if you look at your hand from the back side, you can look across from your thumb to your index finger to your middle finger and remember to always tell a fib F, I, B. Okay, so before we go on to doing examples using the right-hand rule, it'll be worthwhile to just briefly go over the rules for vector negation. So let's say that we have some vector A, and let's say that it is pointing up and to the right. By definition, the negative of that vector, negative A, will point down and to the left and have exactly the same length. We say that these two vectors are anti-parallel, which is just a fancy way of saying that they point in exactly the opposite direction. Now let's see how that applies for looking at the magnetic force. So let's say that we have a charged particle that is going down and to the right with velocity v. Now, if this is a positively charged particle, we would have to multiply the velocity by its charge. So we will need the vector plus e, that's its charge, times v. Well, if I multiply a vector by a positive scalar, I will get another vector that points in the same direction. It won't necessarily have the same length, and in fact, because the units are different, comparison of the lengths is meaningless here. Now let's say that the particle is a negatively charged electron or something like that. Let's say the charge is minus e, and so I will need to find the vector minus EV in order to figure out which way to point my index finger. Well, again, I will take V and multiply it by E, so I get a vector exactly this long, but because it's negative, it will have to point in the opposite direction. Okay, so in the first example we're going to look at, we're going to assume we have a uniform magnetic field that is pointing into the screen. So the X's I'm drawing here represent the magnetic field lines that are coming in from above the screen, penetrating through the screen and passing out underneath the screen. So we will label these as B, and the little crosses should tell you that that's like the feathers of an arrow flying away from you. So our field lines are pointing into the page. Okay, so now let's say we have a positively charged particle, and it is moving to the right at some velocity v. Now before we can find the direction of the magnetic force on this, the first thing we have to do is figure out for our proton here what q times v will be for that. So in this case, it's a positively charged proton, so the vector that I'll need will be plus e times v. So that will be a vector that points in the same direction not necessarily the same length, and again, comparing lengths is meaningless here because they aren't the same units. There'll be a vector also pointing to the right of magnitude EV. Okay, now that we can do that, we can go ahead and do the right-hand rule that you should be seeing pop up in the upper right-hand corner of the video here. And we will find that the force is pointing up. Okay, now in our second example, we're also going to be taking a look at a charged particle moving to the right in a magnetic field that's pointing into the screen, but now the particle is negatively charged. So what that will mean is the first thing we'll have to do is find out what the charge Q times V is. Well, if it's an electron, the charge will be minus E times V. All right, so the big deal here is that this is going to be negated. So we'll first multiply V times E. We'll get a vector, say, yay long. And then we'll have to flip its direction. So minus E times V points to the left. Again, it's not meaningful to compare the lengths here because the units of E times V and V itself are different, so length comparison is meaningless. Now, when we go ahead and do the right-hand rule for this, what this means now is we'll have to point our index finger to the left. You'll then have to rotate your hand around, keeping the index finger pointing left, until the field fingers point into the screen, and then you'll find that your force thumb is pointing down, so the magnetic force is down. In this next example, I'm going to take a look at what you do if the velocity of the charged particle is not at right angles with the magnetic field. So just to help us think about things here a bit, I'm just going to draw a plane that the velocity and the magnetic field will be in. And once again, here we will imagine a positively charged particle moving to the left. And we will imagine that the magnetic field is coming out at some angle much bigger than 90 degrees away. So for us to get the magnitude of the force, this here would be our angle alpha. And we would say that the magnetic force in magnitude would be equal to QVB times the sine of alpha. Okay, but when we're doing the when we're trying to do doing the right-hand rule to find the direction of the magnetic force, you recognize that V and B aren't at a right angle. It's not a big deal. Still go ahead and point your index finger in the direction Q times V, so we need to figure out what that is. And again here, because I will be multiplying by a positive charge, plus E times V would also be pointing to the left. So now what you'll do is you'll go ahead, point your index finger to the left, rotate your hand until your index fingers are pointing out of the screen, and then if you want, you can curl your field fingers just a little bit to get it to line up perfectly. In any event, you should get that the magnetic force is pointing up. In our last example here, we'll take a look again at a magnetic field and a velocity that are not perpendicular. This time we'll have a negative particle going to the right. So in this case, again, because it's a negative particle, we have to find what Q times V is. So let's say this particle is an electron. We'd multiply by its charge, negative E, multiply it by V, and we get an arrow pointing to the left. So when we do our right hand rule, this means that we'll have to point our index finger to the left. You'll rotate your hand until your field fingers come out of the screen pointing towards you. And again, if you desire here, you can open up your field fingers just a little bit to get a perfect fit. But again, in any event, you should find that the magnetic force is pointing up.